Thank you for agreeing to join us for this series of interviews, Harry.
Well, real pleasure, Jim.
We normally begin by trying to find out a little bit about people's background. And where did you come from? What was your early education?
Yeah, well, I grew up mainly in Gravenhurst in Muskoka, and so I attended Gravenhurst Public School and Gravenhurst High School. I guess I did pretty well throughout my early years, and I did particularly well in math and sciences. So after I graduated from grade 13, I was accepted into the engineering physics program at the University of Toronto. It was well known that the engineering physics program was an extremely demanding program at that time. It covered all aspects of math, physics, and chemistry. In addition to that, it covered all the engineering disciplines. It was really intended to provide a very broad base for graduate work in what is now normally regarded as STEM disciplines. So I graduated in 1965 with a degree in engineering from the University of Toronto.
Okay, and full disclosure here, Harry and I were both students for AECL in 1965. There were about 400 students that year, and I came a little bit late. I was doing a master's degree, and the beds were pretty packed in Champlain House, and I took over the bed that Harry vacated because he just got married at that time. So I know his wedding anniversary pretty closely. What did you do in 65 here?
Well, after I graduated from U of T, I was looking for a summer position because I wanted to return to University of Toronto for my PhD work. At that time, as you probably know better than I do, that the AECL was working on a very large accelerator called the ING project, which coincidentally was the same as my surname.
Right.
And the initial concept was actually to have a linear accelerator to produce protons up to about 15 MeV, put it through two cyclotrons, the first one taking it up to about 120 MeV, then the next one taking it up to about a GeV. Then it was put into a storage ring before they strike the target to produce neutrons by spallation. There was actually a need to see the proton beam, to allow people to align magnets,
right,
and to study beam behavior due to changes in beam energy or magnetic field and stuff like that. As you know, when you have pass a current in a wire through a magnetic field, the wire bends because of the Lorentz force, similar to a proton beam going through a magnet. In fact, there's a unique relationship between the energy of the protons and the current and the tension of the wire. So my task at that summer was to study the so-called floating wire method and to develop the equipment that was needed in order to apply this particular method to the ING accelerator. So during the summer, I developed a frictionless air pulley, and I developed a scanning magnetic probe, a Hall probe, and then I used that equipment to do experiments and do measurements, actually using a pole face of the Van de Graaff that was taken down in the physics division at that time, and I basically confirmed that the floating wire method was completely valid, and at the end of the summer, I wrote a big report. It was called the use of the floating wire method to simulate the proton beam of the separate orbit cyclotron.
Very good, because I'm afraid I haven't seen that one before. You will know that after ING got cancelled, sort of,
Yeah.
I then spent the next 20 years of my career on remnants and looking at things of that in accelerator physics. So yes. Yeah.
Oh, it was I mean, it was a fascinating proposal.
Yeah.
I mean, if the government had gone ahead with the ING project, I mean, ACL would be in a different position.
Okay, then you went back. You got your PhD in Toronto, and you came back to Chalk River in
1969.
'69. Okay.
Yeah.
And you started work with, was it Bill Cross at the very beginning, or?
Yeah. Actually, it was fortuitous that I ended up working with Bill, because after that summer in '65, my intention was to do my PhD at the University of Toronto, and then come back to Chalk River to work on an intense neutron generator, and to perhaps do neutron physics. At that time, the University of Toronto had just finished building a state-of-the-art LINAC,
Right.
and they were, and my interest was actually to study sort of neutron physics. It's a bit interesting how I got into that because I was sort of, interested a little bit in reactors. And I thought to myself, well, in a reactor, you produce the neutrons using fission, right? And so fission neutrons are fairly high energy. They are of Maxwellian distribution around 1 or 2 MeV.
Right.
But reactors operate with thermal neutrons, right? At 1/40th MeV. That's 8 orders of magnitude between the energy of the neutrons you produce and the energy of the neutrons that you actually use. So I said, I wonder what the neutrons look like in between. This is called the intermediate neutron energy region. Right. I went around the entire physics department and asked the profs, what does this region, not a single one could answer that question. So I said to myself, I'm going to find out. So that was my main interest, actually, in my graduate work. Actually, the LINAC source, the way that produce neutrons, a bit like what the ING project was supposed to do. So I was actually doing the studies. I studied the neutron spectrum from the source using neutron time of flight, and I did both my master's and my PhD thesis related to the interactions of those neutrons with various materials.
Right.
So unfortunately, of course, the ING project got canceled in my second year. But fortunately, when I was about to graduate, Chalk River was actually looking for neutron physicists to do something called neutron dosimetry. And of course, I was in pure physics, right? I didn't know anything about neutron dosimetry. So I looked into neutron dosimetry, and I found that it was a wide open field. It was crying for somebody to come in and do something to improve the state of the art. Right. So I took the job, actually, in the health physics division. And so I changed from pure physics to more applied physics. The health physics division was a very small, health physics branch was a very small branch. There were only 5 research scientists backed by technical staff. And everybody was working on their own little area. And Bill Cross was actually very interested in betas, okay? But unfortunately, because there were a lot of work going on neutrons, he got pulled into neutron dosimetry. And I think Bill really wanted to get somebody to do neutron dosimetry so he can go back to betas. So I think he was probably instrumental in hiring me to go into the branch. So naturally, when I joined the branch, I worked closely with Bill, and it was a very nice collaboration.
For many years, actually,
Yeah.
it continued on very well. And there were, when I was looking up, there were a lot of publications of you with Bill, et cetera, and well, I guess Bill continued for his own research for many, many years. It
Yes,
was,
yes. Actually, I really enjoyed my collaboration with Bill. Bill was just a wonderful individual, for one. I mean, we actually became quite good friends. But Bill was a very solid, theoretical, experimental scientist, step by step,
Right.
very logical. He was interested in the betas because he did his PhD in quantum scattering. And
Yep.
people tend to stay with,
Yes.
carry on with their PhD work. But anyway, I mean, on the other hand, in my approach to as a scientist, I'm a little bit more intuitive. So I tend to sort of come up with some crazy idea, then I would give it a try. If it doesn't work, then I go back to theory to find out why it didn't work. Okay,
Right.
so we complemented each other. It was really great to have somebody working closely with somebody and bouncing ideas off each other. We did a lot of publications during the years I was there, but most of the publications actually were in what I consider to be theoretical neutron dosimetry. I was actually doing both theoretical neutron dosimetry and experimental neutron dosimetry. And the theoretical neutron dosimetry was a lot easier to get in a lot of publications.
Right.
And that is actually coincidental, because what happened was, about that time, at the computer center, the CDC machine was powerful enough to do something called Monte Carlo
Right.
simulations. Now, Monte Carlo is just using the computer to simulate the interactions of neutrons in any sort of media,
Right.
using cross sections and probability distributions. And so, and at the Oak Ridge National Laboratory, just at that time, they had developed a code called the O5R code, which uses Monte Carlo. And the reason that the people at Oak Ridge developed the O5R code was primarily for radiation shielding design. But in fact, if you have a code that tracks neutrons, you can use it for just about anything.
Right.
Okay, so in fact, it would be a powerful method for reactor physics design as well. In fact, I got the code and I implemented on the CDC machine. So I end up running the Monte Carlo code in ACL all by myself. But then I realized that I finally had the tool for me to really explore what happens when fission neutrons go through various media
Right.
to produce thermal neutrons. So I had just had a lot of fun, So I was running fission neutrons through water, and wow, yeah, this looks just like the time of flight spectrum that I measured,
Okay, yeah.
Then what happens when it goes through concrete? I run it through
Right.
concrete, and then the spectrum changes. What happens if it goes through iron,
Yeah.
And so I was just doing all these, and finally I had the tool for me to answer the question that I was trying to get an answer to when I entered graduate school.
Right.
But it wasn't just strictly for my own fun. The reason is that because neutrons cover 8 orders of magnitude in energy, there is no neutron detector that can cover the entire region in any spectroscopic way, even now.
Right.
Okay. So a typical neutron detector might cover thermal neutrons, like a helium-3 counter or something like that. A fast neutron detector, some sort of scintillator with a discriminator to cut out gamma rays, might see the fast neutrons. But there's the entire spectrum in between that's not been covered by any neutron detector. And in fact, it was, in my opinion, very, very important for radiation protection to have an understanding of what the neutron spectrum looks like.
Agreed.
Because if you're using a meter and you know you're in a reactor, it's in a water environment or a concrete environment, you know you're only sampling neutrons above a certain energy.
Yeah.
You're missing all those neutrons that are also contributing radiation dose.
Right.
And I used to say, if you don't know it, you're guessing it. Okay. But if you know the spectrum, you can make a better guess
Right.
than you can if you don't know the neutron spectrum. So actually, the simulations that I did, which I publish each time, eventually was a couple of years later was compiled in an IAEA report, which I co-authored. It's interesting because as a result of all those Monte Carlo calculations, AECL got to be extremely well known as a center of neutron dosimetry expertise. And you'd be surprised what that does. It opens all kinds of opportunities. I mean, all of a sudden, some of the best people in the DOE labs were talking to you. You're invited to go into meetings
invitations
and
to
all this
meetings,
sort of
yes.
stuff, right?
Yeah.
So it put neutron dosimetry in AECL in a completely different
Yeah.
field. So it was a great. It was a great time to be doing that sort of thing. Yeah.
If we jump ahead about 15 years, then all of a sudden you're concentrating on one particular detector. Can you tell us a little bit about the background for the bubble detectors that became so important?
Yeah. The bubble detector came out of my experimental side of my work in AECL. As I said, when I first joined, actually the neutron dosimetry, in my opinion, and everybody else's opinion, was that neutron dosimetry was really not adequate to meet the requirements of radiation protection. Okay. We were using a film, photographic film of a special type called TNA film, and they were, worn in the badges of AECL in those days. And so what you do is you take the film every 2 weeks and you process it, okay, and then you use a darkening of the film as a measure of the neutron dose. First of all, the energy threshold of the NTA film was above 1.5 MeV. So it was missing even all the fission, most of the fission neutrons. And then it faded. It depended on the humidity during the exposure in the summer. It faded differently from the winter. It was just it was just a terrible dosimeter. So everybody was trying to find a better dosimeter. And there's something everybody, the AECL including, but they're already throughout the world, were doing was something called damage track detectors. A damage track detector is very simple. It's basically it's just a piece of plastic like Lexan or CR39. CR39, in fact, is what they use for plastic lenses of your eyeglasses. If you take a piece of CR39, okay, that we usually use about a one square centimeter, 1 square inch foil, and you expose it to neutrons. The neutrons interact with the plastic, and it causes damage to the structure, to molecular structure of the plastic. After exposure, if you take that and you stick it in hot caustic solution for a few hours, and you look at the thing under mild magnification, say 10 times magnification, you see little pits beginning to that form.
Little tracks from the
little
neutrons.
tracks.
Yeah.
And these, of course, are the places where the neutrons interact and cause the damage. So you count the tracks in order to measure neutron dose. In some ways, it was a lot better than the NTA film, but unfortunately, the damage track detector was also limited to neutrons above about 1.5 MeV. Okay, so there was all kinds of effort throughout the world to try to improve the etching process to make it more sensitive, maybe push the threshold down to maybe 1 MeV or below. Okay, and in Chalk River, when I joined, there was a visiting scientist from Italy that was working with Bill, and they were doing something called chemical etch of the plastic. Basically, what it was is during the etching process, when this thing was a hot caustic solution, you apply a very high alternating electric field. And the thought was that you were sloshing the stuff, the solution in and out of the pits in order to clean it out. So hopefully it's a little bit more efficient.
A bit more visible.
And maybe that will improve the energy response. Unfortunately, it didn't make much difference. It didn't seem to make much difference. I should just explain a little bit about neutron dosimetry, why it's so important to measure lower energy neutrons. The biological damage from what I would call fast neutrons, say around an MeV or so, is 40 times the damage from neutrons, thermal neutrons or neutrons in the intermediate energy region. And the curve of damage versus energy rises very rapidly, and it reaches about half of its maximum value at about half an MeV. So it is absolutely critical, if you really want a good neutron dosimeter, to be able to measure down to about at least half an MeV.
Right.
Okay, and that's why everybody was trying to get the threshold down from 1.5 MeV down to 0.5 MeV. Anyway, it was during those types of experiments that it sort of dawned on me that the reason that nobody can detect neutrons below 1.5 MeV is there's just not enough energy in the neutrons to cause the damage, right?
Right.
Okay, so it doesn't etch, it's not damaged. Yeah, so I thought that in order to detect these neutrons, you gotta somehow store energy in it somehow, because then the neutrons can act as a bit of a trigger, and then the stored energy would cause the damage. Okay, and so the idea of using superheated liquid as a source of stored energy came to my mind. Now, just to provide a little bit of explanation on superheated liquid. Superheated liquid is a very common phenomenon. Normally, when you boil water at your house at atmospheric pressure, it boils at 100 degrees. But if you have a very clean pot, very clean water, and you heat it up very slowly, you can take the temperature of the water above 100 degrees and it does not boil. You might be able to take it up to 102, maybe even as high as 105. At temperatures above 100 degrees, that liquid is superheated. And at that time, if you sprinkle a bit of salt in it, the whole thing would just explode. Yeah. Okay. In fact, it was a common problem encountered in industries that deal with pressurized fluids through pipes. This superheated phenomenon that people were dealing with. Anyway, so the idea came to me that you gotta maybe use something like a superheated liquid, into the plastic somehow, and you don't want the whole plastic to blow, right? So what you really want is little pockets of that stored energy.
You keep the evidence. You don't want to throw it all in the pile.
You want to provide those little pits, right? But I'm not a polymer chemist, and unfortunately, EngPhys didn't provide any courses in polymer chemistry, so I was sort of stuck. Right? We used to the health physics branch is part of the biology and health physics division, and we of course used to have lunch together, the whole division, and we had our own table, right. Typical of ACL. Yeah. So one day I was sitting across from my good friend Chaim Birnbaum. Actually, Chaim was trained in medicine, but he never practiced, and he was doing DNA research at ACL in the biology branch in our division. So I said to Chaim, I said, you know, Chaim, I wish I knew a polymer chemist. You know, there's something I really wanted to try. Okay. So Chaim looked at me. He says, well, I use something called polyacrylamide in my work all the time. He says, actually, it's a 3D cross-linked polymer, but it's not as strong as your normal plastic because it contains water. So it feels more like Jello, but it's much harder than Jello. Okay, but it is a polymer. I said, oh, maybe we'll give it a try sometimes, Chaim. Okay. So about 2 weeks later, I grabbed a bottle of contact cleaner for electronics, you know, for cleaning electronics, and I walked over to Chaim's lab. I said, "Okay, Chaim, let's give this a go." So Chaim prepared his ingredients, polyacrylamide ingredients. This was all prepared in dry ice. He does this all the time, I guess. It was all set up. It wasn't so. So I said, okay. I said, I'm gonna spray some of this cleaner in here. So, then just to make sure that I didn't have little puddles inside, I took it up and I shook it, and I put the cap back on and put it back in the water. And Chaim says, we'll take it out and warm it up and polymerize it. He says it'll be ready in less than a couple of hours. So I said, oh, okay. So. So about an hour and a half later, I walked over and I collected this little vial with that was just prepared, and I walked downstairs to my neutron source, and I took the cap off and I put the detector close to the source, and the entire polymer crawled out of the tube. So I said, wow. I went upstairs and said to Chaim, I said, Chaim, we've done it. Chaim said, what did we do? I said, we have just established the fundamental principle of the bubble detector. Okay. Of course, there was a lot of work to be done because I had put way too much Freon into the polymer.
Too much energy coming out.
Yeah, a lot of things to jig up, right? You got to optimize the superheated liquid to be used. You have to optimize the polymer to contain it, because the viscosity of the polymer has an impact on this performance. Then you got to do the measurements to see what the response functions are like. It involves experiments using a Van de Graaff accelerator to monitor jet neutrons, et cetera, et cetera. So I knew there was a lot of work to be done. But when I told the branch head, George Cowper at that time, what I had just done, he jokingly said, I want my shares. And ACL realized that this actually had commercial potential. And they said, no publications.
Right.
Okay, this has got to be kept quiet because we have to apply for a patent first. Okay, it took about a year for them to get a patent. So finally, after they got a patent, and by that time the detector had been developed to a much more mature state, I made the announcement of the bubble detector at a nice conference in Acapulco, the Solid State Nuclear Track Conference. The announcement of the bubble detector just just spread a wildfire across across the track community. I was told by somebody afterwards that, and I wasn't at the second meeting because it was held in Italy somewhere, that it wasn't even on Dunwich track. They said the topic around the fountain was the bubble detector. So that was the bubble detector, the way it came about.
Okay. Then some difficult decisions came along. ACL decided that this needed to be made into something that could be sold, and
actually what happened was around the time that I was developing the bubble detector, for the first time in history, AACL faced financial cutback in its traditional funding from the government. For the first time in the history of AACL, the government asked AACL what was the Canadian taxpayer getting for the hundreds of millions of dollars that we have been dumping into AACL. And AACL management went into a panic. Okay. In fact, you may remember one of the vice presidents getting everybody about a need to find ways of justifying their existence. And he at one point said something I remember. He said, "I wish I knew how to put a dollar value on every publication we make."
Right.
So AACL found it very difficult to justify, despite the fact that AACL was pumping out a lot of first-class research publications every year, and AACL was regarded as one of the leading research institutions in the world. So management finally said that maybe we would like to spin off businesses, because business spin-off, technology spin-off, is something that maybe politicians
Right.
might understand, and that's easy to understand as well. So there was that famous speech by the president of AACL at the Chalk River Tavern, where he said that AACL was going to be spinning out businesses to maintain the economy of the Ottawa Valley, despite the fact that the funding for AACL was going to be cut, etc., etc. So, in order to identify spin-off businesses, AACL hired a consulting group,
Right.
who went through the entire company to talk to various people. Of course, like an enthusiastic scientist, I was telling him all of the stuff I was doing to bubble detectors and what the implications were. I was told later that the consultant said that a bubble detector was by far the best technology ready for spin-off. So I got picked. Okay. So they wanted to develop the detector quickly. So they formed the bubble technology unit in order to, you might say, fund it at
Sort
a
of
level
incubator
that,
business units they were talking about. then, yeah.
apart from the
Yeah.
traditional funding to the various branches. That was
Right.
why the BTU, the Mobile Technology Unit, was actually formed.
Right. You then had some difficult decisions. You had worked as an academic essentially for many years. You were being asked to get into something that was completely different. You were leaving a pension plan. You were doing some very, very big decisions. I mean, you had a fairly young family still at that time.
Yeah.
Tell us a little bit about the difficulty of those decisions.
Actually, I was quite happy as a researcher. I mean, I was invited to interesting places to give talks. I was quite enjoying myself. I didn't particularly want to be in business, right? So I thought that maybe, within the BTU, I can sort of develop the detector to a state where it's ready for commercialization. Okay, but whether I lead the technology or somebody else leads the technology can be decided later.
Right.
Okay. So it was. So I was not sure what was going to happen to this and who was going to be doing this. So I set up the BTU as a triumvirate, basically with me as a technical director, because I wanted to work and finish this bubble detector as fast as I can, right? So there was AACL appointed a manager for the unit, and then appointed somebody for looking after sort of commercial aspects of the
Right.
of the device. It didn't work as I was hoping. It turned out that I was not able to have the full time of my technical staff in order to develop the technology quickly because of meetings and all this sort
Right.
of stuff. And then there was one particular incident that I remember that made me realize that the idea of having somebody commercializing this besides myself was probably not possible. And I actually got a call from Frank Zabel, who at that time was the head of radiation physics at the Department of Defense at DREO in Ottawa. So Frank said, he said, Harry, where the heck were you? I said, what do you mean, Frank? He said, we got notice that somebody from Charles River was coming down to talk about the bubble detector. So I rounded up a whole bunch of guys to come down to hear your talk. He said, we showed up and you weren't even there. He said, there was some guy we'd never seen who was trying to do a sales pitch on us. So I was not even aware that was happening. So I apologized to Frank. So I thought, wow, this is, not going to work the way I want. Furthermore, AACL, in making sure that this technology had some future, actually did a marketing assessment. And they had a manager to accompany me as we went through Europe to explore potential customers. And as a consequence of that trip, the manager came back and said to AACL that the technology was so closely tied to me that he didn't think that anybody else would have the credibility in trying to commercialize this, because I was known to all the players.
Right.
Nobody else was. It was too technical. There was another thing that I thought I might try to do. I thought I would try to operate the BTU inside AACL while leaving it as a profit center.
Right.
Okay. And I thought we were doing very well because we were getting orders from all over, somebody wanted 100 detectors, this one wanted 50 detectors, and the commercial guy was looking after all this. So I thought, hey, we're making money, right? It was going fine. And then AACL came down. He said, Harry, you got to stop all this. Why? We're making money. He said, he says, we're losing money big time on your orders. He said, every order that comes in has to go to 3 vice presidents for signature. Okay. He said, we did an assessment of the processing time and cost, and it cost over $10,000 to process every one of your orders. So you got to realize
the old story of AACL overheads.
You got to realize AACL was set up to sell reactors at hundreds of millions of dollars,
Yes.
right? It was not set up to sell all the widgets.
Yeah.
So I said, okay, none of this is going to
Yeah.
work. So faced with those realities, I finally said to AACL, okay, so I am going to personally try to commercialize the detector myself, and I will lead the spin-off myself. So once that decision was made, it moved very quickly. AACL wanted to relocate outside and look for venture capital and all this. Let me tell you, the spin-off effort was, as Howard Ray said, it was mission impossible. There were no presidents, right? And as a government operation, you go by rules, but there are no rules to follow. People didn't even know whether AACL had the mandate to spin off a technology. Maybe we have to get an order, an order in the council in order to know whether we have the authority to do this. What was going to be the relationship? Can we have shares in the other company, or some other? Can we treat the company any differently because are we in conflict of interest with other businesses? All kinds of things like that. Yeah. And all this was perking all throughout us, so it was really like the blind leading the blind, right? So anyway, fortunately, the president sort of was say, well, I guess I'm willing to take all of the if there was possible negative blowbacks from this. He said, I want this to happen. I'll take the blame. So anyway, so the thing moved ahead. So we started looking for venture capital to privatize this. And of course, then I tried to look for to a place to relocate outside. Deep River was proposing to build an industrial park,
right,
just at the entrance of Deep River to houses. but that would take 2 years, you know. And I thought, well, that's a long time to. Furthermore, there were a lot of requirements. There was a book about this thick. What were the requirements for the, because as a result of Deep River, gone around to see all the industrial parks and come up with a final design for the industrial park with Deep River. There would have to be so many trees per so many square feet, etc. Right, and the building has to have has to have like a solid wall up to 4 feet and all this sort of stuff.
Parking and drainage.
Yeah, and all that. And I thought, wow, this is pretty demanding. I was more interested in trying to find business to sustain the operation rather than worrying about the specifications on the building that needed to be built. So. Anyway, the only building that was available was in Chalk River, the old hardware store that got burned, and the owner was in the process of rebuilding it, and it was almost livable. Okay, so I rented that building. In fact, there was another reason that I thought Chalk River was a good location, because the reef, Bob Sagan at that time, was very pro-business. Bob came over one day and said to me, he said, Harry, he says, I'm the reef of Chalk River. You must have 100 things in your mind right now. I want to give you my card. He said, you need anything from me, 24 hours a day, just call, and I'll be here. So I thought, wow, this man knows business. Okay, so I really like Bob Sagan. Anyway, I relocated the BTU into the new building in Chalk River. I think it was in the fall of 1987. And then we started to look for venture capital and other things and business possibilities, opportunities in order to try to privatize the operation.
Yeah. Okay. There were a few announcements in the company AECL Review with all kind of events happening and eventually official openings and all of these, and it was good to see. A lot of people at the plant certainly followed that, and I think a lot of people were very proud of what you were able to accomplish at that time, in spite of what all the complications were. So you started out, and really it was the bubble detector that was your item. But over time, then things have expanded and changed. I know that a lot of the things that have expanded and changed have been ones that are proprietary. You have customers, a wide range, but can you give us an idea of how much of the situation now is bubble detectors and how much is other research work for other people? You know, is it 50-50 or?
Well, actually, no. Actually, in the time that has changed from the time that we're opening, the company has really shifted in different directions. Actually, bubble detectors represent a very small fraction of our only a few percent of our sales. Actually, the company is now very much still an R&D company, like the way it was before. I've always wanted the company to have basically two components. One is R&D, and the other one is products. And the R&D will produce products that hopefully will be commercialized by the product side of the company. It still operates like that. From the very beginning, of course, as you say, it was a bubble detector, but very quickly we moved into electronic products. In fact, one of the probably the one of the early you might say accomplishments of BTI was actually building handheld dosimetry system. You may remember that at that time, if you're doing neutron spectroscopy, you have the sensor, you have the electronics, and then you put it in a multi-channel analyzer.
Right.
And the multi-channel analyzer was about 2 feet by 2 feet by
Right.
2 feet. They're big things, and they're lab instruments. And about the time that I was leaving ACL, the emergence of microcomputers came on. And the first one you might remember was the Atari.
Right.
Okay. So what we did was actually replace the multi-channel analyzer using an Atari computer. And so now you have the probe, a small probe of electronics, which could be made as tiny as possible to almost negligible size. And then you have the Atari. So you all of a sudden have a spectroscopy system which used to only be done in the lab, something that you can carry around in your hands.
Right.
So we were the first, actually, globally, to introduce, you might say, dosimetry using spectral measurements, which is, of course, much more accurate than they use of a Geiger counter or a piece of plastic when doing no neutron spectroscopy.
Right.
Okay, so that was called the microspec line of products. We actually had several probes, one for gamma rays, one for neutrons, one of betas, and and you can plug the various probes in. And it was actually I call that spectral dosimetry, and it actually really shook the entire dosimetry world, because they were all still selling handheld little meters, right? It took actually only about 2 years for our competitors to copy that. And actually, I found that not only did the competitors copy it, but actually the governments supported those industries that were developing it. Our competitors provided fierce competition. Their governments actually supported the industry. Canada did not, actually. So I learned a hard lesson, actually, about the Canadian market and the way the company, the government actually operate in terms of the support of emerging technologies. So that was one of the products that we had early. The other product that we developed was something called RoSpec. This was actually a very sophisticated neutron spectrometer. And it was built under funding from the Canadian Department of Defense, the U.S. military, and the French military. All three groups threw money into our project to come up with this spectrometer called RoSpec. RoSpec was actually intended to measure neutron fields for under conditions of nuclear warfare.
Okay.
For instance, NATO at that time was interested in finding out could they do something, for instance, to the lining of tanks that might reduce the radiation exposure from a nuclear explosion, maybe by a factor of 2 or something.
Right.
It's actually good to know that if you expose somebody to high doses of radiation, we're talking about acute radiation, and if you're around 200 rads, what we call 200 rads, you can just you don't have to worry about the guy. He'll survive. But if you expose somebody to, say, 600 rads, you just make him comfortable.
Yeah.
He's going to die. Okay. So there was this little big region between 200 rads and 600 rads, where under very good medical treatment, you might be able to save them. And that
Increase
sort
the
of,
survival rate enormously, yeah.
yeah. Anyway, so you can see that if you reduce the radiation exposure to half the level, I mean, you can save a lot of troops. So that was why that was, and so RoSpec was actually made to fit inside go through the whole of the tank. So they do measurements inside what lining, and so we were deeply involved with that project at that time, and it became the official NATO neutron spectrometer. In fact, after couple of years later, after we were developed this instrument, a lot of the people in the DOE labs heard about it, and so they wanted us to develop similar systems for them, but not for nuclear applications, but for calibration of sources and this sort of
Right.
thing. So I got permission from NATO to be able to provide this instrument to national labs around the world, actually.
Uh-huh.
So this is still regarded as you might say, as the ultimate reference for accurate neutron dosimetry. Yeah, so we still actually sell RoSpecs. It has evolved a little bit over the time, but it's not significantly. So that was another thing that we developed. So as times went on, actually, the microspec line of products emerged into a evolve into a lot much
Right.
bigger system. It is now called the FlexSpec line of products. And these are detectors that fit inside the back of vehicles, police vehicles, and helicopters, inside the helicopters, and sometimes under the helicopters, on boats, for measurement of very low radiation exposures. They're actually used.
But not necessarily just neutrons, it's,
No.
yeah.
In fact, they measure gamma exposure as well as neutrons.
Sure.
And they're actually used by the law enforcement communities throughout North America. So in fact, there are pictures of the FlexSpec line of products in our website. So we're going to see what they look like. So we still, for instance, we still have RoSpecs, we have FlexSpecs, and stuff. But some of the interesting products that we have developed over the years have actually been deliverables associated with the research contracts. We've done really crazy things in those contracts. I mean, we built a system that was able to detect alpha particles at a distance of over 1 kilometer. Alpha particles travel that far
Yes.
in air. We see them at 1 kilometer. At the competition, at a runoff of all the participants, the competitors were just blown away. We have developed systems for Canadian Space Agency with the encouragement of NASA to measure neutrons in space. Actually, the bubble detector itself has flown over 24 missions in space.
We actually have one that we show all our visitors proudly and tell them about it, and then we all ask the question about these guys who are going to be going to Mars without an atmosphere between them and the sun. How cooked are they going to be?
They're actually, there is in fact, it's interesting because it was the bubble detector that first established that the neutrons were a hazard to manned space flight, because earlier models of radiation in space said there were no neutrons, because of course neutrons decay 15 minutes, right? Half-life. So there's not supposed to be any neutrons up there. But then what happened was actually the Soviets who actually wanted to go to Mars by the year 2000. And that was, not far from the time that we were actually spinning out. The scientists, the radiation scientists, told them that you can go to Mars, but our cosmonauts may not come back alive, okay? Because they said for some weird reason, we find from our biosatellites that there are signs of neutrons up there. So our models don't seem to be right. Okay, so we don't understand why this is the case. That's actually why the Soviets came to Canada to work with BTI in order to find out where the neutrons up there and how are they created. It finally dawned on everybody, all the theorists, that if you are inside a satellite, you have high-energy protons. Everyone knows,
Right.
in fact, they're well measured, striking the aluminum shell of the satellite, and you have a NP reaction, a PN reaction. So you produce neutrons as a result of interactions. So it depended on the mass.
Locally produced.
Yeah. So all of a sudden, people said, we forgot to put the satellite in our models. So they put the satellite back in, and everything was fine. But it was because of the measurements that we did with the bubble detector.
Oh.
Actually, Canada and the Soviet Union signed an agreement for peaceful research in space. And the reason that they wanted to do that was because they wanted to use a bubble detector.
Right.
When the Soviets, remember, came to visit BTI, it was all over the local newspapers.
Right.
Astronaut flies into Chalk River and all this sort of stuff. But we, in fact, one of the first measurements that we did using the bubble detector, in a biosatellite, it was an international meeting. The Americans were there as well. We measured a dose, and then at the meeting to discuss the results, people thought that they didn't believe my results. I was up there. I said there are neutrons up there, and the dose is this much, etc. And then all of a sudden, all the guys, there were about 100 guys in the meeting, murmur, and I knew a lot of the guys. And I was at a stage. I said, hey guys, I said, what's the problem? One of the theorists says, he said, Harry, he said, there must be something wrong with your experiments. He said, all our models said there were no neutrons in space. And I was a bit miffed, I said, look, guys, I may not be a space scientist, but I know neutrons, and I can tell you.
I measured them.
You thought I walked off the stage being a little miffed with everybody. Yeah. The next morning, we were staying actually at the meeting was in St. Petersburg. Next morning, I was going down to Catherine the Great, opulent surroundings. Next morning, I was going down to for breakfast, and I heard these footsteps running behind me, and I turned around and I saw the Soviet theorists. They said, Harry, we've been up all night. He said, we made a terrible mistake. He says, we forgot to put the satellite into a model. Anyway, both NASA, I guess, and the Soviets went and put the satellite back in and got the radiation dose. Yeah. So as a result of that, actually, very close relationships with the space program.
Right.
But now, and then that led to something called the CHENS. Which is a very large spectrometer that was supposed to fly in the NASA was going to fly on the bay of the shuttle, and unfortunately that did not happen because the mission before ours was supposed to fly was the mission that they had the shuttle disaster, and after the shuttle disaster they canceled the shuttle program, so that never flew. So anyway, there was some intent to try to make a smaller version of that for future missions. Of course, right now we are actually designing the payload for the lunar mission to look for water on the moon. This is an ongoing program. Of course, water is very important if you're going to have established a moon base for exploration of the various planets. But we have done many things. I mean, we have made quantum scattering that are sort of by coated aperture to focus, to be able to identify a little source of radiation at a large distance. We demonstrated that at the MIT campus. We have built, of course, we built a landmine detection system where we use neutron interrogation of the ground in order to determine whether or not there is actually a landmine in the ground. That was considered to be a big success. The Canadian military was very happy with the results. We've just done a lot of very interesting things over the years. The research is the R&D contract research is actually very interesting.
Good. You started out with a building. There have been a few expansions, and when we drive by there, there's a lot of cars. How many employees typically do you have now?
Well, we typically run around in the sort of mid-50s for the number of employees, and actually in the field of work that we're in, the market is not like you're selling computers or something, so the market is very specialized and very small. In fact, it's very difficult for a very highly scientific company to get to be really big because the market is a very specialized market. But yeah, we have probably in the order of about 50 some odd people usually.
And you've had quite a few ex-ACL people who have retired. In some cases, in other cases, have left the company to join with you, and it's been
Yeah, actually, at the beginning, there were two people in particular that were crucial for the startup. One was John Yevchuk. And John retired a few years ago, and unfortunately he just passed away a couple of years ago. He was the guy that actually made the bubble detectors. He was Hein Birnbaum's technologist, and he, when he came out to BGI, he continued to look after the production of bubble detectors to meet sales. The other person that came out of ACL was Kim Kandari, who now Kim Tremblay now. Kim was actually my, you might say, my right-hand man. I mean, when we were doing experiments in Aberdeen Proving Grounds for NATO, I mean, Kim was there, doing all the setups and doing all the measurements. When I was at the Soviet Union discussing things with the for the Institute of Biomedical Problems, Kim was there, taking notes and all the conversations that were. So she was just an amazing assistant, and without her, I would not have been able to manage all the things that were going on at the beginning. A little bit later, Don Tennant, after he retired from ACL, joined BTI, and Don became the manager of electronic production. He was involved in a lot of stuff. He brought a lot of expertise that was very useful to us. And during his quite long tenure, actually, at BTI, he set up a very strong production team for BTI. And then, of course, there was Bob Andrews, Dr. Bob Andrews, who came to us from the physics group in ACL. He came after the ACL closed the world-renowned physics division. A lot of the scientists, of course, left to
Dispersed all over.
to the United States. In fact, the United States government set up a special program to hire the Chalk River scientists. So Canada lost a lot of talent. But Bob did not want to go to the States, and so he came to BTI instead. And over the years that he's been at BTI and is still with BTI, even though he's getting to be pretty old, he's even a bit older than I am. He has just made enormous contributions to sort of coming up with new ideas for R&D, and then working with the staff in order to develop the to execute the programs satisfactorily. And then a few years after that, Dr. Vern Kovlovsky joined us from ACL. And Vern is just a remarkable scientist. He has unparalleled capability in using mathematical analysis of data. In fact, I knew that Vern was very good because he won a lot of honors when he was in AACL.
Right.
And so to this day, actually, he plays a critical role in a lot of the R&D projects that we have in AACL. So, of course, there are a lot of talented people that did not come to us from AACL, but that joined BTI, people like Ted Clifford, who are very bright, especially in the area of electronic design. Ted has moved over to electronics and was the manager of electronic design and software for many, many years until he stepped down a couple of years ago. So now he's just back to doing basic research. We're actually blessed to have such a talented pool of people. And even our clients who come to visit us have commented on what a well-coordinated and powerful group that we have, because we cover such a broad spectrum of activities in a relatively small company.
Right. Now, you're a fairly modest person, but both the company and you personally have internationally seen a number of honors over the past few years. I see something in the paper every once in a while. Could you just mention a couple of them? Or?
You know, I'm not a sort of guy who sort of craves for recognition, right? I mean, I just like doing my thing, and I'm happy doing my thing. But yeah, over the years, certain honors have come along. In fact, I was, I guess, the first recipient of the Discovery Award by the Atomic Energy of Canada. In fact, I think the Discovery Award was conceived as a result of the bubble detector. And then a few years later, when we built the landmine detection for the military, we've got an award from the Canadian Nuclear Society for the conceptualization and the innovative applications of the technique, or something like that. BTI itself has won a lot of honors and awards over the years. Too many to mention. I mean, for instance, when we worked with Raytheon, we got the award for the supplier of excellence. In fact, Raytheon, when we were working with them, actually the president said send his vice presidents up to BTI for a day, because he said he wanted his vice president to see how a good company is run. So the ridiculous thing is that you have this private jet that flew into Pembroke Airport, and then you have about half a dozen big shots coming in, milling around for a day. and then they take off. It created chaos. But in the year 2020, I was awarded the Meritorious Service Cross by the Governor General for starting BTI and advancing the field of radiation detection. And that was a ceremony that was held down in Rideau Hall. Apparently, I didn't know very much about the award, but it was established by Queen Elizabeth II. It was supposed to be one of the highest honors for a civilian in Canada. And then a couple of years after that, in I guess 2022, I, as well as BTI, was inducted into the U.S. Space Technology Hall of Fame in
Excellent.
Colorado Springs. And,
Congratulations.
and that was for the invention of the bubble detector and its use for radiation monitoring of astronauts. Apparently, it's very unusual for them to give this sort of honor to a non-American.
Yes.
Because all the other recipients seem to be associated with NASA in one way or another. So it was an unexpected honor.
Yeah.
But anyway, but I don't really take these honors. They don't go to my head.
Well, they're good indications of how you have contributed to the field, and we congratulate you on all of them.
Yeah.
Okay. Age eventually catches up with all of us a little bit, and you have backed off a little bit. There's very, very few of us have been able to do what you have done, and that is to pass the torch over to someone in the family. So
I was always very reluctant, actually, to be involved with the with the future of my children, for good reason. Because if they fail, I don't want to be the guy that they want that bears the blame. Okay, so in the case of Leanne, I don't have to worry about it because she was actually hired by the board of directors over 20 years ago. When I was approaching the age of 65, the board of directors was worried that I was going to retire. And then they found out that I had a daughter who was just finishing her PhD at the University of Toronto. And so they actually called her to ask her whether she was willing to join BTI in the event that I retire and perhaps run the company. And to my surprise, she said yes. I was really surprised because I know there were a couple of oil companies that were just waiting for her to get her PhD to grab her. So, but actually, she took the offer from the board and came up to BTI. So she's been with the company for over a couple of decades now. And in fact, over the last 10 years, she's essentially been running it anyway. I find that everybody's going to her instead of coming to me, so okay. So a couple of years ago, I formally sort of stepped down, and then she took over, but it was not a big change. She was quite ready to, and everybody else in the company was quite ready to. So the transition occurred very smoothly. I still go in actually 3 days a week, but I don't stay the whole day. So I probably in total is only a couple of days in time. The reason I do this is because I have seen in the research community that that a lot of scientists spend their entire life learning everything in a particular field and become an expert in a field, okay? At sometimes at great expense to society. But then when he retires, all that technology disappears. We see that in ACL. I mean, I see that I was on the board of directors of Triumph and also of Canadian Light Source for many years. I saw it in all the research labs. And I didn't really want to see this in BTI. So I wanted to extricate myself very slowly, trying to pass the information on to the next generation to the extent I can. But in fact, it's not easy.
And one of the things BTI has to work on is a memory dump for all the seniors.
Yeah. It's not easy because, Jim, the problem is that at BTI, we have people that come from different universities, and they are under different training. So I don't know what they don't know, you see. So I can't just teach them something because they may already know it, right? Yeah. Somebody else may not. So it's very difficult. So what I've actually resorted to do is I just sort of make myself available. And if they run into a problem and they think that I know the answer, they come up and talk
Right.
to me about it.
Yep.
Okay, and I can try to answer the question. But if they don't, if I get to the point where nobody wants to see me for a week or so, then I know it's time for me to just forget about going in. Then that'll be the end of it.
Good. Well, I did a quick mental calculation, and since your PhD, you've been at this for about 56 years. I think we just have to treat that as a remarkable career, very, very successful, and thank you very much for sitting down with us.
Well, real pleasure, Jim. Thank you.
Right out.